Hi, this is Dr. Kaushik Pal from Chandigarh University. I'm working as an associate professor at University Center for Research and Development, Punjab in India. I would like to thank my colleague who is organizing international conference CONBRA PA 2022, my dear friend Professor Fernando Gomes de Souza. I have a lot of years collaboration with Professor Fernando, and we are dealing with several projects, several books, editing, and previous conferences, and we are planning for upcoming events. So I really grateful University Federal Rio de Janeiro, all associate members appreciating me as a international convener of your nice conference, CONBAP PA 2022, which is now going to held 24 to 26. I would like a grand success of this international event, and actually this platform for only for academicians, scientists, young research scholars, those who get an good platform for exchanging their innovative research ideas, joint publication, and most important is a strong collaboration to know each other so that we can grow together for our innovative projects. So I really thankful to all the members, the associate with UFRJ, Rio de Janeiro, Brazil. Regarding this international conference, I would like to start my presentation in nanotechnology and material science related research background for practicing in laboratory scale to industrial scale. I think my innovative talks will be helpful for young researchers, scholars, and all the associate members, and I'm really happy to uh, collaborate with all the person worldwide. So I am just now trying to share my video presentation with you all. So just I'm sharing my screen with you. Let me start with PowerPoint presentation. So today's my talk on novel materials horizon in nanotechnology, academia to industry practice. So I basically from material science and liquid crystal research background, and I'm also working on biotechnology, polymer, synthesis and switchable device, optoelectronics, graphene nanotechnology, and green energy generation, solar cell, and several fields. So from my slides, I'm trying to give a feather touch of all those kind of flavor of research so that people can, I mean, multidisciplinary research can attempt. And I'm happy to collaborate with you all guys. Thank you so much. I'm starting my presentation. The, I'm from Chandigarh University, leading as a associate professor and group leader. So at University Center for Research and Development. So my content of my talk, brief introduction of technical research expertise, and I will discuss about my fundamental research backgrounds and how you will can approach for the material science, graphene, liquid crystal, assembly, hybrid composite, polymer composite related research for industrial utilization, as well as I will show you hand-on expertise on micro nanostructure fabrications and analysis, and my scientific innovations I will share with you for your yeah, I mean ideas, research ideas, and application. Mainly I'm interested different kind of applications and benefit from our research outcomes. I will show my research projects, patents, and few achievements which I achieved in my professional and research career. My ongoing research activities and with Malaysia, with others, reputed institute. I will show you my honors and professional achievements, aims and scopes, future development for the laboratory setup, how to do that, and I will of course acknowledge my group members and worldwide research communications. So actually, what is nanoscale? Nanoscale is a very basic things. It's a 10 to the power minus 9 order. It is a one part of a billion of a human hair, and you can see that nanotechnology is such a versatile topic nowadays, that we can move forward into biology, chemistry, material physics, material science, polymer, photochemistry, catalysis, drug delivery, clinical application. There are so many things, and of course, is a biomedical field is a most important craving ideas is nano robot. Is a yeah, it actually around 5 micrometer, and once it insert your human body, so it can monitor our blood pressure, blood sugar, as well as by extra collagen and fat they can diminish, I mean they can extract from our body, and we can just monetizing it externally after inserting. Is a very small nano robot in our body, and it's a very huge application in Netherlands. Of course, my colleague is working collaboration with me. So and benefit of nanotechnology is a lot of things we can should acknowledge that water lily is a super hydrophobicity, and sometimes self cleaning for the surface roughness, and the textile industry, the glowing of our t-shirts, that can be using of TiO2 nanoparticles coating, and scratch free windows and cars, and sometimes we use the antibacterial coating by TiO2 for in hospital windows, and also we can apply for our screen treatment. You can see here, that's two lady for the screen, how to use the titanium dioxide after treatment and before treatment, how we do that. And my innovative research basically on nanowires, nanorods, nanoparticles, nanospikes, nanocabbages, nanoflowers, and sometime we incorporated some hybrid nanorods and porous nanorods, core shell nanostructure to our host materials. And we can also doing those kind of nanomaterials for spectroscopic and microscopic evaluation. After confirming the morphology, then we can just doping with our hybrid nanocomposite, so our electrical and optical properties completely change, and different of morphology, so we will get the different kind of research outcomes and information that we can implement for our new device. It's called a nanoscale device that we can do. And basically, we wrote some projects regarding on that. Liquid crystal, nanometal dispersed liquid crystals, or graphene dispersed liquid crystal is a source, and for mainly efficient switchable device on and off state, how to work our sample in the device, that I will show you. My additional work based on helpful for the PhD and postdoc scholars. So first, what I did, just we synthesize our basic bulk material. We started with salt, and then we can our motivation to size and shape dependent morphology. So that's why we use some surfactant. Let's say polyethylene glycol or CTAB is a surfactant. Sometimes we use the hydrogen hydrate, which is a capping agent that should accelerate our chemical reaction. and sometime it when you are approaching some chemical experiments, so sometime the nanomorphology is not growing very smoothly, sometime obstruction is there, some cluster particle will be there in the reaction time. So those kind of surfactant will help for the smooth growth of your whatever you are looking for the morphology, let's say rod, sphere, particle, or hollow sphere, whatever, so that we can easily perform. So though after just chemical synthesizing process, we just go for the x-ray. First we do the FECM, field emission scanning electron microscopy, then we will do high resolution transmission electron microscopy, and what kind of materials is there, that should be detected by EDX spectra. Then we can go for the chemical mapping also, and surface morphology is analyzed by AFM, and also we can take the surface current, how much current passing through the surface, that can be also measured by CAFM conducting mode, CAFM, let's say, and X-ray photoelectron spectroscopy, UV visible for absorption spectra, photoluminescence spectra, Raman spectra, laser spectroscopy, and we most essential microscopy is a polarizing optical microscopy, through which we can see the phase transition of our material undertaken inside the switchable device. I will show you. And also we are working on let's say a polymer, polarizing optical microscopy, and impedance analyzer, the dielectric spectroscopy for measure the dielectricity, and IV measurement for Kitle source meter, and semiconductor characterization spectroscopy, and multi-scale nano device for graphene sensor and optoelectronic smart display, we can easily utilize. And go for the next. What is a liquid crystal? Actually, liquid crystal is a very interesting molecule, which is a distinct phase of matter observed between the crystalline solid and isotopic states. So liquid crystal generally have several common characteristics, let's say rod-like molecular structure, region of long axis, and easily polarable substitutes. And when we doped with nanomaterials, so it's showing a very innovative research outcomes. Let's say optical properties and dielectric and electrical properties drastically changes. And there are several of phases. Let's say smectic, nematic, and smectic A. We at the time of temperature, that it is gradually changes. So it's a very interesting thing. So this is our experimental confirmation of our different kind of morphology, like TiO2. We have started with TiO2, zinc oxide nanorods, CDS, and you can see the different starting material we used, different shapes and morphology. And after that, when we disperse CDS into liquid crystals, that is a microflower like structure evolved. And then the bunch of nanowires accumulated and aligned as a microflower like structure. And those you can see here, the nanocubes and nano spikes, zinc oxide, and this is a liquid crystals, hydrogen bonded liquid crystals, just worm like structure you can see here, these two sides. And this is our graphene nano sheets. When it is dispersed with the liquid crystal, it's a nano fiber type attachment is obtained after same morphology when we confirmed it. So this is our novel electro-optical device. So here, what we did, this is a ITO coated glass substrate, and inside we insert the sample, and it's a commercial value is $10, and is original making cost just $1 if you made in lab scale. So it is a brand new cost-effective electro-optical switchable device technology. Then it is very flexible. We can handle any type of samples inside the cell, and two electrodes will come out, and you can see polymer dispersed liquid crystal, graphene dispersed liquid crystal, nanometers dispersed liquid crystal, any hybrid composite or sometimes nanometers, you can just put inside its capillary action. You go inside and from two electrodes we measure, we just supply some sample bias voltage. Then under polarizing optical microscopy, it actually shows on and off states. I will show you through diagrammatically how it is working. And so this is I just started very simply, chemical ingredients, let's say zinc, CDS, zinc oxide and titanium, and it's a alkaline media. That it's a clear transparent solution is there after stirring. So when we transferred to another beaker and we introduce some hydrogen hydrate for the reducing agent, that should accelerate our reaction rate, and it will help us for the smooth growth of our nanomaterials which we are looking for. So those prepared transparent, fully transparent solution, after starting 20 minutes, you can transfer it into autoclave, Teflon line autoclave itself. It's a, just a 60,000 gallon pressure will diminish the bulk property, and we will finally obtain the nanomaterials. It's a nanoscale order, and we just first filtrate. After that, from when the autoclave come in room temperature, then we can very carefully uh, come out our autoclave, Teflon autoclave. Inside the sample is there, so we can filtrate and several times washed with ethanol and ethanol. And DI water, double distilled water, so that the impurity is completely gone, and we can heat it up in our furnace, so that the impurities and ethanol completely evaporate, and we will get the our powder like sample. Those powder like sample, little moisture is there, so we just dry it for our oven, electric oven itself, for 4 hours at 40 degrees centigrade. Then we can get the final desired powder like sample, that is called our nanomaterials. So you can see, I started with CDS, cadmium acetate salt with sulfur powder, and we use the ethylene diamine EDA. So we started at, and you can see in the naked eyes how the color is changes from dark yellow after 20 minutes stirring using the PG, polyethylene glycol, and then yellow greenish solution is came after stirring. So that after that, this solution we just transferred into autoclave to prepare the CDS, high quality CDS nanomaterials. So you can see it how the we tune the rod to flake. Yeah, you can see here the diameter and length is we can tune gradually, and we our confirmation by FESM. So that article is already published in Applied Surface Science. So we also prepare the silica gel, tetraethyl orthosilicate, HCl, H2O, pluronic, ethanol. We just make a ratio. In this ratio, we make a clear, transparent solution, pre-hydrolyzed solution dropwise. Why? It is for silicon coating, for high reflection. Silica gel coating is required for high reflection. That's why we prepared this silica gel coating. And this is polymer, polymer coating. Why it is required, I will discuss. 6 nylon balls dissolved under trichloroethanol for the 3 days continuous stirring, and there will be a polymer solution will be obtained. And you can see we just coat it on the substrate of the quartz substrate or glass substrate. After that, we can grooving in the rubbing motor, so that proper grooving, so nanomaterials will be aligned very distinguishedly and properly. Otherwise, it's just coagulated. You cannot distinguish those nanomaterials inside the. I mean, just over the quartz substrate or glass substrate. So here you can see I used the spin coater, programmable spin coater for thin film deposition. And here you can see the SiO2 coated glass substrate. What is the morphology? And here CDS, after this SiO2, then CDS nanowires dispersed on the substrate. You can see the high resolutions, the microflower-like structure evolved, and this is a zinc oxide. And also this porous, some unreacted parties come out, so the porosity is appeared, which is detected by FESM. And this article is published in Journal of Molecular Liquids and Journal of Molecular Structures. Different kind of series of experiment we published here. This is a TiO2 nanowires. It's a basic material. We started with bulk anatase TiO2, so that we can different kind of phases is there, is rutile, brucite, and anatase. So basically we started with anatase. So you can see here a lot of in XRD there is a lot of rutile peak, impurity peak is there. So several time washing with the HCl, same procedures which I previously discussed. So same procedure, hydrothermal process. So you can see the rutile peak already gone after annealing. So ultimately we will get only the anatase. So it is confirmed by FESM is a 1.5 nanometers diameter, very ultra thin nanowires, and 700 nm length of the nanowires we observed. So it's a very novel work, and we can apply it for doping with a WF182 antiphylactic liquid crystal for nano cabbages. With the nano cabbages, I will show you. So you can see the self-enhanced controllable growth dynamics of zinc oxide microflower structure to my nanoparticle. So how we can tune the same procedure but different material. So we easily you can chemically tune the morphology of several materials, so that optical properties, electrical, dielectric, optoelectronics, every properties will be changed drastically, in fact. So here I did the same thing, that I just inserted zinc oxide with the liquid crystal. You can see the cavities got the cavity, and inside there is a particle. So this is kept by the liquid crystal molecules after annealing. So, and this is a novel switchable device. It's called a electro-optic switchable device in a surface stabilized ferroelectric liquid crystal device. You can see first what we did when we insert the our hybrid liquid crystal and nanomaterials materials inside the cell, and it is just passing through the inside the cell. And you can see with the temperature, of course we apply the bias voltage, 0.5 volt, and also we connected with the temperature controller. You can see different kind of phases, is a crystalline, is a smectic C, smectic A, nematic, and isotropic. And a different kind of switching mechanism with that temperature variation. You can see it is completely stabilized with it is hybrid composite with a liquid mixed with the nanomaterials and liquid crystals, is a stabilized states. Now after employing the biasing, so how the switching is appeared here, it is an internal mechanism. We captured this video through polarizing optical microscopy camera. So and a different kind of phase, it's called on state and off state. So switching of ferroelectric liquid crystal dispersed tetramethyl and ammonium bromide CTAB assisted CDS nanostructure. How we introduce this material, similar hydrothermal process, and we made the deposition of liquid crystals into this Felix liquid crystal, I think. And also we measure the characteristics of polarizing optical microscopy. You can see the oily droplet structure and shell line pattern and mosaic structure, everything is formed. So sorry, and this is our polarizing optical microscopy. Yeah, and this is our Chinese group is working on this zinc oxide material, nanospike itself. With a smectic liquid crystal, and we published in Journal of Material Chemistry C. And you can see here the on state, off state, how, and this is the rubbing conditions of our cell, and how you can see the how after rubbing direction, so how the molecule is organized properly. And here the switching is the on state and off state I showed. And this is another technology. It's called vertically aligned nanowires. So first we obtain the seed particles. So first the seed particles, when it is obtained, then within these seed particles we vertically aligned the nano wares by thin film deposition is a programmable spin coater, and we also take the field emission. So how much length will be sharp, so we will get very ultra thin sharp nanowires will get high emission. So that is most important for this case. So in this technology, you can see the FECM structure is a vertically aligned zinc oxide microflower structure. Is a bunch of nanowires, and is gradually formed. You can see here is gradually formed. This is a microflower after annealing, and at 650 degrees centigrade, this is a nano rose form like structure evolved. So those kind of series work we published in American scientific publishers, and for this flexible polymer dispersed liquid crystal module with a graphene electrodes, how we made the same procedure. And this is a sodium assisted TiO2 nanotubes array, where array for the novel electrodes for photochemical sensing platform. Is the same strategy we applied for highly aligned TiO2 nano watts and nanotubes itself. You can see how we aligned those things in the substrate and anodization process, and immerse into NOH solution, and simply electrochemical cost effective method, we easily detect this sensing, photochemical sensing itself. And this is actually functionalized graphene oxide dispersed hydrogen bonded liquid crystal for electro-optical switching. So this is I produce in this magazine that very high quality nano ribbons. Graphene is called graphene nano ribbons, and how it can be applied for the smart display technology. So it is actually published in Journal of Display Technology. So appreciate our work. And this is, you can see the switchable and self-assemble CDS nanowatts embedded liquid crystal for high performance static memory. You can see many people say working on liquid crystals. These things is a pure liquid crystal. You can see the resolution. Resolution is very slow. When this is a pure liquid crystal, when we disperse liquid crystal into our nanowatts, high quality nanowatts, you can see easily our resolution is how increase. So we can it's called contrast ratio. Through dispersing of nanomaterials, our contrast ratio is very high. It is measured by oscilloscope. You can see the graph, contrast ratio versus time. So that these materials later appreciated our work. And after when I just applied the sample bias, that resolution is as it is when we remove the bias. So it's called it's just behaves like a static memory device. We can use it. So this is a dynamic application of novel electro optic switchable device modulation by graphene dispersed liquid crystal assembling CDS nanowatts. So here we can see the flexible film we used, electrode frames we used, and you can see the how it is working. And this is our smart in-plane switching of nanowatts embedded liquid crystal matrix. The same things, but different material we used here. And we measure the surface current, and through AFM you can see the surface current. However, we measured through these experiments. And this is actually our liquid crystal device, which we made in our laboratory scale, that it is very simple to hydrocoated glass substrate we just sandwiched, and before that we make a thin film, and we properly aligned after grooving the liquid crystal and nanomaterials, and we just two electrodes come out, and you can see the on-state and off-state when it is placed under cross-polarizing optical microscopy. And Journal of Journal of Material Science, Materials in Electronics just appreciated our work, and this is actually called our emerging self-assembly zinc oxide nano wires graphene dispersed liquid crystal for switchable device modulation technique we used here. And my USA group, UK group is associated. So hands-on expertise on solar cell, basically solar cell for R&D companies. You can see the solar cell for R&D companies were applied for this where silver we use the silver nanoparticles. So that is you can see where high yield silver nanoparticles is there. We can use the HR10 and everything. So and it's an aggrandized efficiency of ultra-thin topical cluster silver nanoparticles, and it is very compatible. We can fold it up, and it is very portable device. We can it's called portable solar cell efficiency is 79.55%. So we can use it and aggrandized efficiency of ultra-thin efficiency of solar cell. And this is a short self assembly of liquid crystal for superior switching application. This work is very interesting. We just incorporated our theoretical ideas as well as experimental ideas. You can see here some electro-optical phase transition studies we here and yeah, this is experimental studies in on and off states and simulated patterns of molecular orientation in different state of matter, solid, liquid, to isotropic, that we measure and that we just calculated by simulation pattern through theoretically actually. So and this is another work is organic electronics, and 2020 is a reliable optoelectronic switchable device implementation by nanowires conjugate bend core liquid crystal we mainly tried. So that is the most important things we I mean implemented for our switchable device is a most is a first work, and several countries group people is associated with me for this. And this is actually broad carbon family, I mean carbon nanomaterials synthesis and emerging application we can try to implement through this article. And different of you can see go through this article, you can show see the how much application this is diversities of application we can do by your carbon nanotubes. And this is a biodegradation of vascularized SBR for this comparison between our work that should be published in scientific reports with my friend Fernando. So and this is our sol gel technology also appreciated work for structural dielectric optical investigations and nanomedicine. One of my colleague from Malaysia, here she's working with nanomedicine. And these are biochemy is a virus like nanoparticles novel gene therapy, that is also work done with my collaborator from USA Michael and my postdoc from Jason from Katin University Malaysia. So and this is our screen treatment. We just use the aloe vera gel for peel off mask formulation by cosmetics industry applying for the green nanotechnology. It's a very simple and cost effective technology. If you go through this article, and you will really, it's very interesting how you can make the screen treatment and all. So this is our very hot topic nowadays for the topical review on nano vaccinology and biochemical process for key challenges. You can see the we control the SpO2 saturation level very low during this COVID affection. So now we can boost our immunity booster is a 91% by using such for vaccine using the vaccine and all. So this is a vaccinology technique we published in Process Biochemistry, and you can see the synthesis of green nanomaterials and green chemistry for the biogenic application. For a kind of biogenic application, we can utilize from the basic taramine fruit, and for we synthesize the gold nanoparticle, but it is very costly if we started with the ascorbic acid. So if we rather we will try from taramine fruit for chemical process, and just easily we can synthesize the gold nanoparticle that can be applied for nano imaging as well as drug delivery, cancer treatment and all we can see here. And this kind of work is published in Materials Today Chemistry with my Malaysian group and Egypt group and Slovenia group. So we can try it with citrus fruits, mushroom, and some green is a cost effective green nanoparticle synthesis from the natural extract. How it can be implemented for the biomedical sciences biogenic application that I implemented in this paper. And this is molecular structure for the bioplastics, which is a very hot topic. Also, bioplastics is a tensile strength. How we can tune, and how you can synthesize for this kind of packaging application that I implemented is from IKTP in Sepang, Malaysia, with my group, Dr. Karan. So is my another work in COVID and ivermectin for the human use during this our pandemic situation. We just implemented this work with Mexican group. And this is graphene face mask. This is called sunlight sterilized graphene face mask, reusable graphene face mask for sunlight. It's very easy, very cost effective, and we can use from the COVID virus or any type of virus we can protect. It's called a very highly efficient sun. It's also coated of polymer and graphene. And execution of viable application for self-guard against viral infection for conflict. This comprehensive review is done by my postdoc, is for antiviral coated face, is called the face mask for this global pandemic situation. And this is a one critical reviews we wrote that on nanographene for the nano imaging and biosensor application. It's a very excellent presentation how we can use the sensor for different kind of biogenic application. If you go through this, you will understand how important this is. And this is another cutting edge development of on graphene derivatives by liquid crystals and CDS TiO2 hybrid composite, how we can implement for the optoelectronics device as well as biotechnological aspects. So this is my contribution of books and chapters, which we almost 25 books I edited, not yet updated here in this list. So this is our published book. We published more than 28 books, and with my colleague Professor Fernando, also with me as associate editor, several books. You can see here nanofabrication and application of smart nanosensor, and another book is also here, multidisciplinary sciences and advances. We have a lot of work with my friend Fernando. And I should acknowledge my research members, those enormous contribution for my research career and academic development. Those they are helping a lot continuously in my research career development. So this is my scholars Jason, and from Malaysia and Egypt, Kerala, UK, and Exeter, Netherlands. So my PhD scholars are also working on this group, and some of my master students in China and South Korea, Brazil, is effortlessly work very hard with me, and we published more than 140 research articles, not yet update here. So, and book around 25, we edited 28, and patent research 5. And I'm the editor in chief in several international Elsevier and Springer journal. And we organized international conferences, workshops, and lectures, and I attended around 38 international conferences. And institutional and academic development, I should must acknowledge some you BTech or MTech nanotechnology, you should focus, every institute should focus on their technical degree, which is most important. And also PhD coursework, module teaching, hand-on expertise, practical demonstration is very much required for the research development. So I always encourage all the institute should develop with a new course of studies, which try through current, based on current research programs and motivational research skills training programs. We can do summer research program, winter research program, some scholar or faculty research program, exchange program. So international publication, and most thing is that important thing is that international conferences, that is platform for exchanging the knowledge and ideas, that people should understand each other, try to collaborate, and lot of projects and public joint publication we can do. So, and future planning for the training and development, in our university and research organization, that is our ongoing my research on superlattice work. So that is very innovative research I just trying to develop. And here we also did the POM, polarizing optical microscopic switching studies and thermal studies, and this work is ongoing. And also this is our graphene transparent electrodes we made, and automobile industry, fuel, solar cell, renewable energy, optoelectronics, smart electronics, polymer technology, biodegradable mass formulation, sensor nanotechnology, wastewater treatment. There are a lot of several aspects we can utilize this kind of technology using nanotechnology, graphene, polymer, and bio-inspired materials. So this is our current work based on 2021. We optical shuttering action. So some people is working on the glass substrate. I just tried with a flexible PET sheet. You can see here how I will show you some video that will confirm how our optical shuttering action working. So you can see the novel is a novel optical PET sheet here. This is actually novel application for the graphene liquid crystal. How to implement for the industry, and how is made for the first made in the lab scale, then how to industry. And you can see that my colleague is working on the glass substrate. When it heat it up, then trinary mixture of liquid crystal, when we heat in the hot plate, then it just you can transparent opaque film, you can see the opaque film is there, yeah, you can see that. But same thing I tried in my studies is a flexible PET sheet. You can see here the opaque simply opaque film is there. So by trinary mixture of liquid crystal, so when I just made in a hot plate, so you are, and it's a very flexible, you can see now it is very completely transparent. So it's actually flexible sheet. And also we can apply for the 3D printing technology, flexible display. So and this is the graphene biosensor. You can see the sensor, how it is working for the tribo electric tribo nano generator. reserve for energy harvesting. You can see here the thing, and we can for the automobile industry display LEDs, coating. I already told water resistant tires and everything, and 3D printing technology. We can use it. Graphene biosensor, and also it is most important for the graphene biosensor for the RT-PCR or COVID test virus. How it is working? Yeah, I just implemented this work, and you can see that. How our biosensor is working. We first make the graphene film, a thin film of graphene, and then we made the yeah, transistor. It's called field effect transistor. So grain and grain will be is there. You can see we just several laser deposition technique we made it, and you can see gradually that how the it's a source and drain, and inside our sample will be there, our swab sample will be there. So and there is some detector. You can see that we implement first the graphene, and you can see the after that the Y protein will become and conjugate with this graphene, and with a biochemical bonding structure. How it is working is an efficient sensor. You can see the Y protein is came already, and it is just conjugated, and after that source, gate and drain, that is already implemented, right? And now we are applying some sample inside, and there is a, digital detector is there. You can see uh, you can see how it is detect the sample. There is no sample, so it's a very saturated level, right? Now when we are giving some SARS or CoV2 spike protein uh, is there. You can see some response is there. Sensitive is a 1 Fg per ml. You can see the graphical graph is showing is there by sensing, right? So and then you can see um, yes, MERS CoV2 spike protein. You can see there when MERS viruses came. So what happened? So here is very there is a no response, very low response. So and SARS-CoV-2. So when we concentrate the our virus concentrate, so it is very high peak. Now for now we will try for the human. You can see the response, how it is gradually increases. So now we can use the human swab test, right? So swab test. So what will happen, this is a CoV2, I mean this is a COVID virus person. You can see the swab is so much high, while we tested for the normal person, swab sample for healthy person. You can see there is when swab test there is no response. I think is a there is a no response. So it's it's called a graphene biosensor we implemented. And also the supercapacitor sensor is keen by using the graphene technology, which is nowadays very hot topic, using this graphene. And also charging and discharge graphene self assembly, high efficient battery for the vehicle. So now petrol, except petrol diesel, we can use the battery car, right? So within a second the battery is charges. So you can see the charging level, how swiftly the battery is charging and discharging, how swiftly is working. So and also this is a graphene supercapacitor. And this is our eco-friendly products: agricultural productivity, energy regeneration, clean manufacturing, smart application, R&D, technology, and improve medicines. So this is a skill training program we started in Malaysia also, that should be implemented any research institution and universities, that laboratory chain work, somebody who is working doing experiments, somebody laboratory management, somebody work on synthesizing, somebody data analysis. So is this in this chain work, so we can do some rapid publications, right? So and our incubation center we just developed from 2022 to 2030. So startup incubation center and all, and we are connected with several Indian projects, Spark project, Gyan project, Birak project, Impress. So with collaboration with my colleague Professor Sabu Thomas, Mahatma Gandhi University, and this is our international collaborator agencies, those who continuously support us for the research funding and those kind of extensive research implementation and application for the industry, laboratory scale to industry, that they're helping me so much. And we also did the MOU with different research institution, at least more than 25 research institution. We already make the MOU, and this is my few awards and Marie Curie Fellow and Young Scientist, Visiting Scientist, and I got the DSC from High National Youth Skill Institute, IKTB and Sepang, Malaysia, last 2020 June. Thank you so much for those awards, and this is my visiting scholar research program, and this is visiting faculty in Malaysia, France. This is we are connected with Professor CN Rao, who is a material scientist. We are in the group, so we are working in this group with Mahatma Gandhi University. So and this is some of my colleagues from several institute though invited me as a chief guest. So all group members from China, South Korea, Finland, from Professor Sabu Thomas from Mahatma Gandhi University, this is from Malaysia, Russia, Professor Olava, and this is from University of Malaya. So Professor Director invited me. Thank you so much for your kind attention. And further collaboration, you are most welcome anytime. I am happy to collaborate with you all. And I would like to thanks my dear friend Professor Fernando. And in near future, we can do more physical conference when the situation will be comfortable. I will of course invite you all in India. So in our visit our laboratory. And thank you so much for your support and help.